So if I remember correctly, they have something like this. And they want you to draw the structure. And they're saying that this is the compound. Okay. Okay. So to calculate a formal charge, first off, is I'm going to type it out because my handwriting is crap. So formal charges. And then you'll also see that they also had a typo. It said formal change instead of charge on their question. Formal charge is going to be equal to the valence electrons of that atom minus the lone pair electrons minus the bonds. Okay, so I'm going to save this problem for a second. So I'm just going to put this to the side for right now, and then I'm going to show you what I mean. Okay, so let's say we're talking about this guy. Actually, let's do. Okay, so the way that we would calculate, and you guys can see my dots there. Sometimes people have trouble seeing the dots. Okay. So the way that we would calculate our formal charge is you're going to calculate it for each atom that's in the compound. So we'll start with this first oxygen, call this oxygen 1. Then we'll do the carbon, it's going to be number 2, and then we're going to do this oxygen. Okay, so for 1. Okay, so how many valence electrons does oxygen have?
6.
It has 6 valence electrons. Okay. So then we calculate the number of lone pair electrons. That means these guys here are called lone pairs. So those are lone pairs. Lone pair electrons are the electrons, the number of electrons that are in each of those lone pairs. So if we count each of the electrons above that, how many lone pairs do I have?
2.
Well, I have 2 lone pairs, but how many lone pair electrons do I have? So
4.
how many total electrons are there? 4, that's right, 4. Okay, and then I subtract the number of bonds. How many bonds do I have there?
2 bonds.
So the formal charge on this guy is 0. Okay, now number 2. So number of valence electrons for carbon?
4.
Number of lone pair electrons?
2.
Number of bonds?
Would that be 3?
That's right. So then that would give me a -1 value. Okay. Okay, so 3. Number of valence electrons for oxygen?
6.
Number of lone pair electrons?
6.
Number of bonds?
1.
Okay, so, okay, and actually this compound will be CO2, 2 minus. So that means that we have 2 extra electrons. Okay, so in this case, this would be the formal charges. That's how we calculate the formal charges. Now, what we want to do is, typically we want to try to get our formal charges as close to 0 as we could possibly get it, right? In this case, this is going to be pretty good. It's as close to 0 as we could possibly get it because we had 2 extra electrons associated with this guy. And if you actually calculate it, this is -1 and this is -1. That means that we have an additional charge of -2. There's 2 additional electrons. So your charge should add up to all your formal charges added up together if you have a charge associated. Okay, does that make sense? You guys have it? Look, so that's formal charges. Now, formal charge is the reason why you calculate your formal charge, because we have what we call the octet rule, and then we have formal charges. Formal charges lets us know which structure can be stable, because we could also draw this a different way. There's a couple ways that we could have drawn this. Potentially, there's a couple ways that we could have drawn this. Okay, but we drew it this way instead of drawing it the other way, because this may be a more stable form that we have. Okay, and so if you get a formal charge that happens to be all zeros, it works out perfectly, then, which wouldn't happen in this case, we'd expect this to have a negative charge because this guy has a negative charge, then that would be the best case that you have, that total 0. Okay, are you with me right now? Or is it kind of confusing?
Yeah.
Okay. So now let's get to this problem here, right? Let's see. Can I erase this? Did everybody got this down? But I'll leave the definition of a formal charge out. Okay, so this is the problem that we're looking at. So this is the compound that we're working with. And they started us out, if I remember correctly, they started us out exactly like this. Am I right or am I wrong?
I don't remember. I ran out of my 11 attempt.
Okay, you ran out of your 11 attempt? Okay, so this is how they start us out. Or actually, I think I already did this one. So initially, let me make this correct. This. So I think initially they started us like this. And these guys didn't have anything on them. Okay, so I think it's like this. Okay, this is how they started us out. Okay, and they're letting us know right here, this is what we're working with. So this is what we want to do is, the first thing that we want to do is calculate the number of electrons that we have to work with to do our Lewis dot structure. So bromine has how many electrons?
7.
It has 7 valence electrons. Oxygen has how many?
6.
It has 6. Well, we have 3 oxygens. So we multiply that times 3. So that's what?
18.
And then this minus here, that means that we're going to add 1 more electron. Okay. So altogether we have 26. Is that right?
Yes.
So we're working with 26 electrons. Right now, what we have showing is 6, right? So that's 2, 4, 6, because each line represents 2 electrons. Okay, so what I do is, I know I'm working with 26, so I'm just going to start putting my electrons up. Let's see, we know that oxygen is going to have 3 around it. I mean, 3 lone pairs around it. So that's a total of 6. So then that gives me what, 12? This guy, whoop, that's a, so now we're at another 6, so that's 18. And then I put 1 more. Another 6, that's 24. And then, oops, 24, I need to get 26. Okay, so then now I just want to make sure that everybody's obeying the octet rule. So right now, if I do it that way, if I base it on the octet rule, that's 8 around this guy, 8 around this guy, 8 around this guy, and here, 8 around this guy, okay? Now, that is the octet rule, right? That means that it's based upon the octet. But if I want to make it based upon formal charges, I can cheat. I can click formal charges, or I can calculate the formal charge of each one. You guys know how to calculate the formal charge. So this guy has a 2 value for its formal charge. This guy has a -1, this guy has a -1, and this guy has a -1, right? So that's not so good. Anytime you have a 2, 3, 4, 5, anything like that, you know we've got to find a better structure, okay? So we also know that, or you guys don't, but you will know today. I'm going to share something with you right now. You're going to hate me for this, but can't help it. It's red. So any of these guys that are below period 3, any of these guys that are below period 3, they don't have to obey the octet rule. They can get out of obeying the octet rule, right? They're called exceptions. They can become what we call hypervalent, meaning that they can have more than 8 around them. They can have, in some cases, phosphorus, for instance, could have 5 or have 10 around it. Sulfur could have 12 around it. And so they're able to be a little more flexible. And that's the same thing with the bromine as well. The reason why they're able to do this is because we have the 3D in the third period. So what it is that these electrons, because they're going to be sharing electrons with other atoms, they can actually pack some of those electrons in those upper shells. That gives it a little more flexibility. So they're not limited by just having 8 around them. They can actually go beyond 8. Okay. And I'll be talking about that in a lot more detail today. Okay. So let me get back to my problem. Maybe. Are you guys with me so far? Nobody's gonna jump off a bridge?
Oh, can I get my attempts back?
Yeah, I'll give you a couple more attempts. Don't worry. You're good. You're good. Okay, so now what we want to do is modify this so that we try to get this as close to 0 as we could possibly get it, right? But we also know that we have a negative. So it's okay for them to have one of the guys to have a negative charge associated. And the one that we want to have a negative charge on it is the one that is going to be the most electronegative. We'll be talking about that today again, okay? So the one that is going to be most electronegative in this case in terms of bromine and oxygen is more electronegative. So we want to try to make sure that if it's going to be a negative charge, we want it to be on the oxygen, not on the bromine, okay? So the way that we can do that is we can start playing with, because we know that we have the right number of electrons around here, we can start playing with how we have those guys set up. So I'm going to take this oxygen, for instance. I'm going to drop it down to 4, and then I'm going to make this into a double bond.
So question, Dr. Henry, I thought like oxygen always has to have 3 lone pairs, like when we're doing these kind of problems.
They don't have it. Oxygen could have 3 bonds. So that means it has 1 lone pair, right? All you need is oxygen. Oxygen has to have 8 around it, right? Because it has a strong electronegativity, it wants to make sure it has 8 electrons surrounding it. It has to obey the octet rule. Bromine doesn't have to obey the octet. So that gives bromine some flexibility. So now, by us doing that, if you guys take a look, now the formal charge on oxygen is down to 0. Okay. Now, if we do the same thing over here, and see. So we trade that lone pair for a double bond. That gives us 0. So everybody's 0. Bromine is now 0. Oxygen is now 0. This oxygen is now 0. But this one has a minus. So that's going to give me my best possibility, right? It's going to give me my strongest possibility in terms of formal charges. Okay. And okay, so however, it's not minimized. Okay, so we made that adjustment. Check it out. Bam. It's a little slow. Okay. So I'll give you guys a couple more tips, but that's how you'd go about it. So that's how you would use those formal charges. Now, here's a benefit to you guys. Because you guys are in, I wanted you guys to be familiar with formal charges, so that's why I put it on the homework, but you guys are not obligated to do formal charges, right? Because for 2A and 22, Chem 22, it's not one of those things that I'm going to require, that I require. But I want you to know it just in case you guys decide that you're going to go into general chemistry in the fall, you'll be familiar with it already. And so it gives you a little more strength. Okay, makes you that much better. Okay, are you okay, Brittany?
So will that be on the test or those?
So formal charges officially will not be on the test. However, hypervalency will be on the test.
Okay.
Okay.
So I think I exhausted my attempts on number 48, and it's something similar to that because it does say, I remember it says like formal charges are not minimized, but it also says something with like the least. I can't remember.
Resonance structures. Yes.
Yeah, that one too. I was like, well, what the heck? Like, I think I got the Lewis structure right, but I don't know. I don't know what I was doing wrong. I try to search videos or like Google, and I don't know. I just was like, okay, I got a headache with that question.
Oh, it's all love. I'm very proud that you guys are doing it. It makes me feel good that you guys are picking this up. Okay, so resonance structures will be, it won't be on this exam, but it can be on the next exam. I have to think, where is it on this exam? I have to look. But let me explain resonance structures to you. Okay. So first off, let's talk about the Lewis structure. So if you read the problem, it says the Lewis structure for thiosulfate, and this is the chemical formula for thiosulfate, with the minimized formal charges. That's what they want us to do first, right? So they want us to try to find the best way of showing. And then they're also telling us that how many total resonance structures exist for that one. So first thing that we want to do is draw the structure, right? So in this case, it is more stable to place the negative charge on the largest atom. Okay, so that's our hint. Which one is going to be the largest atom? Oxygen or sulfur?
Oxygen.
Are you sure?
Sulfur.
Okay.
Well, because they both have the same. Well, no.
What is the rule? Remember the trend. Don't throw out our trends. Remember we talked about those trends, right?
Okay.
Do you remember the trends? As we go from left to right, what happens?
Smaller radius, left to right.
Okay.
Okay. Because sulfur's on the same group, but it's low. Okay, never mind.
Okay.
I gotta look at my periodic table.
Okay. So sulfur, yeah. So sulfur's got to be bigger than oxygen, right?
Yeah.
We want to make sure that one of the sulfurs have a negative charge to it. That's what they're basically telling us. Okay. So let's go ahead and try to draw it. Let me find sorry, I have so many windows open. Can't find stuff. So we're going to go ahead and click here. Okay. So we also know that, we don't know, but you will know. Let me explain something else to you. Let's look at the periodic table.
This is about how sulfur likes to be bonded.
What was that?
It's about like how sulfur likes to be bonded.
Yeah, that's what we're going to get ready to explain. Okay, so sulfur is weaker in terms of electronegativity. Electronegativity is the desire of an atom to have the electron closer towards itself compared to its partner. So if they're sharing, so there's ways of sharing. So we could share it evenly. So that means that you get it half the time and I get it half the time, right? Or we could share it unevenly. I get it 90% of the time and you get it 10%, right? So that's kind of like how I like to share, especially when it deals with like games or playstations or anything like that. I play with it 90% of the time. You'll get it 10%, right? It's sharing, right? Because you still get to play with it, but
Barely.
but it's uneven sharing, right? Okay, so electronegativity kind of lets us determine who is going to be stronger, who's going to be the one that's going to, kind of like the bully, who's going to be the bully that's going to take it most of the time, right? Or is it going to be shared even? So even though that they're in the same group, because oxygen is higher, it's going to be stronger. Okay, so that means that oxygen is going to share in a way that is to its benefit, right? So it's going to try to keep it most of the time. Sulfur, as a direct result of that, also means that it's going to be pushed in the middle. So it's going to be the middle atom. So it's going to be the center atom. We're going to have a sulfur in the middle. Okay, now I'm going to go and start drawing our structure here. So one of the sulfurs is going to be in the middle. The other one is going to be on the end, and then the rest of them are going to be oxygen. So this is going to be our middle. It has 4 bonds. Right. Okay, so first thing that we need to do is we got it drawn out. We know that sulfur is going to be our center atom. Now we need to figure out how many electrons we have to work with. So sulfur has how many valence electrons?
6.
So we have 6 times 2.
12.
And then oxygen has how many valence electrons?
6.
6 times
So-
3, 18.
So we'll have 30. Yeah.
But then,
So 32 valence.
Plus 2.
there we go. So we got 2 electrons. So we have 32 to work with. Okay, so then as I tell you guys, the first thing that you want to do is just populate it. Put your 32 around there, and then you can kind of work around with it. So right now we have how many showing? So that's 2, 4, 6, 8. Okay, so then let's just start putting electrons around each of the guys, so that then we'll keep track of it. So that oxygen, if we put 6 around it, so that's
16.
is it 16 or is that 14?
Oh, well, because you added 6. Okay, never mind. I thought you had added
Okay.
8. So 16.
Is that 16 or is that 14?
Hold on. 2, 4, 6, 8, 10, 12, 14.
Okay. And then if we add another 6 to that,
20. 26. 32.
okay. Okay, so we want to try to make sure that we have the smallest formal charge as possible. This is kind of like a little cheat way. We have our formal charges there. This guy's a 2, right? That tells me something is wrong. I need to try to fix that if I can. So, and then all of these guys have a negative. We don't want all of them to have negative. We want to try to minimize the number of negatives we have. So we want to try to get some of these at 0. So we click on the oxygen. We'll drop 2 of the electrons, and then we'll make this guy, right? Oops, wrong thing. There we go. Okay, so then that makes this a 0. That makes this a +1. This guy's a -1. That's a -1, -1. Well, let's see if we can make it even better. So we'll do the same thing here. Okay, so now we got 0, 0, 0. This guy, one of the sulfur has a negative. The other guy has a negative. They both, you add those together, they equal that -2 that's there. That looks like it's good to go.
So question, Dr. Henry. So this
Okay.
having 12 valence electrons. So how much, like, is there like a max that sulfur
Yes.
or any of them could
Yes.
go over?
Yeah, there is a max. So technically you can use all of the electrons because, okay, so let's take a look at the, in theory, there is a max. But usually there's ones that they prefer. Like sulfur prefers 12, right? If it has to, 12 is its ideal. It'll do up to 12. And usually it's based upon how many spots left over in the D shell, right? So sulfur is only 2 away, so there's 2 there, right? So that's 2, 4, 6, 8, 10, 12. Okay, so because of it, it's going to sit there and use that outer shell, that outer D shell, right, to its full potential. Okay, where phosphorus is only going to go up to 10. Okay, so it's usually going to have 10 around it. Okay, does that make sense? See,
Okay,
because
so I'm trying to figure
remember,
out, why did you count the 3D for sulfur?
because it's okay. So it's kind of like sulfur. We're not count. Well, we are counting in 3D. So sulfur is in the 3rd period, right?
Yes.
The 3D is also technically in the 3rd period, even though it's energy-wise, it lines up in the 4th period. Because it's that 3rd energy shell, technically these are like empty seats that you can use if you have to use them.
Oh, okay. Yeah, because I was looking at it more so because when we're doing the when we're like, okay, Aragon and counting,
yeah.
that's like we don't count 3D for sulfur, but okay, now I
Yeah,
get it.
so remember, these guys, this is for bonding now, right? So it's not just looking at where the electrons are located. These are seats for electrons to be shared with. And so it gives it that flexibility. So all of these guys, like I said, the ones that are in the 3rd period and below, these guys can be what we call hypervalent, meaning that they can have more than 8 around. Okay, they can. They don't always do it. They would prefer, if they have a choice, they prefer to be the octet. But if they have to, they will be hypervalent. Okay. But those are good questions. Very good questions. We're ahead of the game. Okay, so let's go back to the problem. Okay, so, and the way these formal charges are calculated, although I'm kind of cheating because I didn't have to calculate each one. If we went through that process, we'll do the sulfur here. Okay, so number of valence electrons that sulfur has?
6.
6.
Number of
Bonds, 6.
lone pair?
0 for lone pair.
0. Okay, and then bonds?
6.
Okay, so that's 0. Exactly what they gave us. Okay.
So that's just part of the question.
Okay. Now
What do
let's
we
talk
do?
about, because that's only the first part, right?
Yeah.
Now we have to talk about resonance structures.
Yeah.
Okay, so I'm going to draw this out again. Resonance structures, because electrons are mobile, so although they're stagnant on the page, they're not moving on the page, really we know that electrons are constantly moving, right? And because electrons are constantly moving, you can end up with what we call resonance structures. So what we mean by resonance structures is basically the electrons are going to be moving, right? And since electrons are going to be moving, the double bond that is normally here, we'll call this oxygen 1, this is oxygen 2, and we'll call this guy oxygen 3. So the double bond here on oxygen 1 could actually be moved so that it's on oxygen 2. So we can move these guys, this guy would shift over, this guy would be like that, just like we did over here. This guy right here. Okay, So, and that will be the same Lewis dot structure, right? It will work out the same way. It has the same number of formal charges and everything like that. The only thing is that we are switching where those double bonds are at, okay? So overall, it'd be the same thing. So since they all exist in reality, this guy exists and this guy exists, it's just a matter of time where you capture the compound at, because the electrons are always moving. Because the electrons are moving, these double bonds are going to be able to switch. So this would be one resonance structure. This would be another resonance structure. Can you guys figure out the last resonance structure?
Would it be with the two double bonds on oxygen, like say to the right, and then the
So would it be oxygen 1, oxygen 2? Where would the double bonds be?
Oxygen 1 and 3.
Okay, oxygen 1 and 3. That's correct. Okay. So that would be 3 different resonance structures. Okay. Now, if we had put the double bond on the sulfur, it actually changes what the structure is, right? Because then, and so that would not be a resonance structure. That would be what we call an isomer, right? So basically meaning it has a different structure, but the same chemical formula. Okay. Okay, are you guys good?
So when we have these, in order to figure it out, you have to just draw them all out.
Yep.
To get the number.
Yep. Yeah, that's the only way of doing it, you know. Okay, so the correct answer is 3. Okay, are you guys good? Yeah, that look.
I think so.
You think so? Okay. Okay, so let's go ahead and get started with the lecture. And the lecture is actually going to reinforce some of these things. I don't know why. I thought I had resonance structures in this chapter, but I think it might. You guys may get a little bit lucky because I don't think it's on the test. So we've talked about the octet rule. You guys are very familiar with the octet rule. We've now talked about lone pairs. So lone pairs are just as a reminder, we did it this guy just a second ago. Lone pairs are the electrons that are not involved in bonding, right? So these guys are obviously involved in bonding. These guys are not involved in bonding, right? So these guys are called your lone pair, right? That's a lone pair, that's a lone pair. Okay, does that make sense?
Yes.
Okay, so for the most part, I'll go, let me. Sorry. Sometimes my keyboard does not want to respond. Okay, see the periodic table? Okay, so as I told you, all the guys that are in period 3, so these guys down, these guys have the possibility of forming hypervalent structures, okay? Oops. Way too fast. Meaning that they could disobey the octet rule. They could have more than 8 around them. They could have 10, they could have 12. I think there's one case where you could actually have 14, okay? But they could actually have more bonds around them than just 8, okay? Now, these guys, they're gonna do their very best, right? 99.999% of the time, these guys are all gonna be, these guys here are going to obey the octet rule. They can't disobey the octet rule. You guys actually have one question that kind of plays with that. So they're always going to try to have 8 around them if they have enough electrons to have 8 around them. Okay? They will never go over 8. Clear.
Dr. Henry?
Yep.
And you said it was called hypervalent?
Yep, let me spell that for you. Valent. Or you'll see hypervalency. You'll see it both ways. Hypervalent or hypervalency. Okay.
Did you just draw on the screen?
No, I typed on the screen.
Oh, I see it. I didn't see the small word.
Oh, let me make it bigger. Okay. And again, I'll bring that up when we start talking more about some of the other exceptions, because there are other exceptions. You'll find chemistry kind of obeys general trends, but there's always going to be a couple of exceptions. You guys are going to be upset about it, but you'll get over it. You'll hate me for about a month, but then you'll get over it. Okay. So now let's talk about polarity. Okay. So polarity is when things are being shared uneven. So we were sitting there talking about it. Remember, I talked to you about like a PlayStation, right? So as a kid, I have 2 sisters. We were poor, and my parents, when they bought a really nice gift, it would be a gift that we would have to share. And my philosophy of sharing would be like, I get it since I'm the oldest. I would get it 90% of the time, and my sisters would get it 10% of the time. I have 2 sisters, so they got 5%, right? So, so that is an example of polarity, right? It's uneven sharing. We're sharing by my mom's rule. My sisters get to play with a toy, but I get to play with it. Okay, so uneven sharing. Okay, now non-polar basically means that things are being shared evenly. So you're getting it 50% of the time, and the other thing is 50%. Okay, so now and in this case, when we're talking about polarity, we're talking about the polarity of the electrons. We're talking about electrons themselves. So electrons are what's going to be making the bonds. So we have what we call polar covalent bonds. Polar covalent bonds mean uneven sharing of the electrons. One atom is getting the electron more than the other. So let's say, for instance, we have carbon monoxide. Carbon monoxide, if we draw the Lewis dot structure, would be like this. Okay, so in this case, carbon is weaker in electronegativity. Also, carbon's goal is to try to make everybody else happy, right? Carbon's a whore, all that stuff, right? So in that context, oxygen is going to be getting the electron around it majority of the time. So we would say that it forms what we call a dipole moment, right? A dipole, where oxygen, the electrons are favoring oxygen. They're going to be around oxygen more than they're going to be around carbon. Okay, so they're going to spend more time around oxygen. They're going to spend carbon. So it's polar, right? The way that we signify this is either by drawing the arrow. There's another way that we it's what we call partial charge. So since we're talking about electrons, and electrons are negatively charged, then carbon is going to have less, the electrons are going to be spending less time around carbon and more time around oxygen. Carbon is going to be partially positively charged. So we use this symbol delta plus, meaning partial, okay? Partially positive. And then that means oxygen is going to be partially negative. Okay, meaning the electrons are spending more time around the oxygen. Okay, so does that make sense?
Even though the structure looks like as if it would be non-polar, like it looks like it's equal, you have to take a closer look at the actual element within the structure to know.
That is correct, yes. Yeah. So now things are going to be nonpolar if they're shared evenly, right? So if we have oxygen bounded to oxygen, which is oxygen is a diatomic, so oxygen gas is always going to be O2, right? They're both oxygens. They have the same strength. So neither of them are going to be favored, right? So they're going to be shared evenly, right? So then that molecule is going to be considered to be nonpolar, okay? So this guy is going to be polar, and this one is going to be nonpolar. Now, again, this is representing, it's talking about the bond, and it's also talking about the molecule. So the bond between these guys here is polar. The bond between these guys are considered to be nonpolar. Now, when we have more than two atoms attached to each other, like carbon dioxide, to figure out if the molecule as a whole, or the compound as a whole, is polar or nonpolar, we'd have to look at each of the bonds independently and then look at them together. So we know from this molecule here that oxygen is more electronegative than carbon. So we could sit there and say, this figure here, that oxygen is going to be favored again, right? So we have what we call a pole going towards oxygen, okay? But we have an oxygen on the other side going the opposite direction, okay? So in this context, it's kind of like your carbon in the middle. You have two twins that are pulling you from both sides, right? So if you have two twins pulling you from both sides, they weigh exactly the same. They have the same strength. Neither of them are stronger than each other. So what's going to happen in that context? Are you going to move in any way?
It's still going to be equal then?
It's still going to be equal. So in that case, it's going to be like equal sharing in that case. So it's going to be equal sharing. So then this guy is going to be a nonpolar molecule. Okay, now, if we have here we have water. Okay, now water, hydrogen is weaker than oxygen, severely weaker than oxygen. So in this case, we're going to have the same situation where oxygen is going to be favored. Okay, now since oxygen is favored, then the electrons are going to be going towards oxygen, right? So this situation, because it's going towards oxygen, it's kind of like you have these twins on the outside and you're in the middle and you're pulling on the string and you pull them towards you, right? So in that context, because you're stronger than both of them together, so you're able to sit there and pull it towards yourself, right? So in that context, the molecule is considered to be polar. Okay, and it's going to be going towards oxygen. Does that make sense?
Yes, they're not sharing. You can only be nonpolar if you're actually sharing something, right?
Well, no, they're sharing because hydrogen is sharing with.
In the sense of like, because it's just oxygen as being the hogger between nothing else. He's just hogging everything.
Yeah, but he's still sharing. Hydrogen gets it, but it only gets it a little bit at a time, right? But you're right. Yeah, in that context, oxygen is like, hey, I get the electrons the majority of the time. You get it, 5% of the time, So, and that's different from ionic, where ionic electrons are being given up, right? They're totally given up. So these guys are just, they're being shared, but uneven, right? So that means that the electrons are still being shared between the two, but the electron remains between the two, but it's spending more time with one than the other. You know, it's kind of like, okay, like this. So a married couple decides they're going to get a divorce and they have a kid, right? So they could share the kid where the kid has spent half the time with one parent and then the other half the time with the other parent. Or if you know that one of the parents is so much better than the other, they're going to spend, 5 days with one parent and then 2 days with the other parent, right? So that's an example of covalent bonding, right? Polar covalent bonding is when you have one parent getting it more than the other, right? And then non-polar covalent bonding is when they share it evenly. So does that make sense? Share that kid evenly. Now, ionic bonding is when you have one parent and another parent, and one parent says, I don't want anything to do with that damn kid. It's all yours. That's your kid. Bye, right? So that's an example of ionic, where the kid gets put on that one parent only. Okay, do you see the difference, right? One is sharing, and then one is give and take. One is giving it up, one is going to be taken.
What would the ionic look like?
So sodium chloride, right? Sodium chloride. So in this case, sodium gives up its electron, but sodium actually is really, it's positively charged. Fluorine takes the electron, so it's negatively charged. But when you put it together, they balance each other out, so they don't have a charge associated.
Okay.
Okay, so ionic, covalent. So covalent bonding only occurs between atoms that are non-metals. Okay, ionic bonding occurs between 99.99% of the time occurs between atoms that are metals and non-metals. So a metal will bond to a non-metal ionic. Okay. So how are you guys doing? It's all there? You feeling it? Yeah, no, maybe?
Hello.
A
Yeah.
little? Okay. Okay, so let me show you a picture. Okay, so we have two X's here, right? Both of these X's are equal in strength. So they're going to share evenly, right? So this guy would be a non-polar covalent bond because it's evenly shared, okay? In the middle, we have X and Y, where Y is so much bigger than X. And so since Y is so much bigger than X, it's going to be pulling the electrons more. So that's the reason why it's bigger, okay? And it's going to be shared unevenly, okay? And then we have ionic, where we just gave up the electron entirely. We're like, oh, here, you take it. So we can be positive and they can be negative. Okay, so those are your three types of major bonding. Okay, so we have non-polar covalent, we have polar covalent, and we have ionic. Okay, so the way that we determine which atom is going to be in the center, if there's multiple, if we're attached to more than just one other atom, is by looking at the electronegativity, right? The electronegativity also determines whether or not we're going to be polar or non-polar, okay? So there's a trend. So electronegativity is going to be increasing from left to right, and then it's going to be decreasing from top to bottom. Okay, let me show you. This here represents the electronegativity, but if you look at the general trend, we get increasing from left to right and decreasing from top to bottom. Okay, So how do I use this, right? So if there's question about polarity, we can actually use numerical values to sit there and help us determine who's going to be favored, right? So let me give you the rules, and then we'll talk about how to calculate it. See if I can write it down right, because I screwed it up last time. So if our number is less than or equal to 0.4, it's considered to be nonpolar. If we are greater than 0.4, but less than 1.8, then it's considered to be polar. And then if we are greater than 1.8, greater than or equal to 1.8, then we are considered to be ionic or have ionic character. Okay, so these both are covalent bonds. This is ionic bond. Okay, now how do I calculate this? So here we have fluorine. Let's say we have fluorine and oxygen, right? So this is a bond between fluorine and oxygen. So we have a bond between fluorine and oxygen. So we take the values of fluorine, whatever one is highest, which happens to be fluorine, and we subtract the value of oxygen. And that gives me what? 0.6. So based upon my little table up here, oops,
Could it be polar?
it's going to be polar.
Dr. Henry, before you continue, for the second one, for the one that's polar, were you trying to say like greater than 0.4 but less than 1.8?
Yeah, it's greater than or equal to.
Oh,
Yeah.
no, the second one, the one that's for polar.
Polar? Yeah.
Yeah.
So we're saying that the value is it's greater than 0.4, but less than 1.8.
I think it would help maybe like if you put like a X or like a symbol for value or something. It looks just a little confusing even earlier. Sorry.
Is that better?
Yeah.
So if that difference is greater than 0.4, but less than 1.8, it's going to be polar, right? And 0.6 is polar, right? Okay, what about, let's say, carbon and hydrogen?
Nonpolar.
Okay, so it would be nonpolar because hydrogen is, carbon is 2.6
2.2.
and hydrogen is 2.2. That equals 0.4. Okay, so what about carbon and sulfur?
What? Still nonpolar? Polar. Is 0?
Okay, yeah, because 2.6 minus 2.6, so it would be nonpolar. Okay, simple.
Mhm. What about when you have like, say, like carbon, like, you know, you have like a little 2 in the bottom, and then
So
like 2
you're only-
carbons, and then will we be doing the math the same way? Like 2
No.
carbons and let's say 2 sulfurs.
Nope. In that context, you have to do between each bond because we're talking about bond polarity, right? So you're looking at each individual bond. Does that make sense?
So we wouldn't add them all and then subtract, no?
No, no, you'd
Okay.
have to do each one differently. So you're saying if you had something like this, right? Right, a molecule like this, you'd have to look at each of the bonds independently.
Okay.
Okay. So, because that's why you want to look at bond polarity, and then you want to look at the molecule.
No, I'm talking about, well, yeah, something like that, but I'm talking about like say we have H2O. You know how we have 2 hydrogens
Yeah,
and 1
exactly.
oxygen?
So
It
in
would
the
be the
case of
same thing, we'll
H2O,
just do it
it's the
individually.
same concept, right? So in the case, so you're looking at this bond first, and then you're looking at that bond. But if you look, then you want to look at the molecule as a whole. Do you understand?
Yeah.
Okay. So you want to look at the bond between it first, right? And you want to determine whether that's going to be polar or non-polar, right? So
Okay.
in this context, again, this guy's going to be polar towards,
Okay.
right? And then that's guy going to be polar. And so overall, the molecule is going to be polar. Okay, does that make sense?
Yeah, yeah.
Okay, so and this is just basically reinforcing that, just telling you exactly what we just figured out. Okay, so, and you guys are already familiar with this. So if we have a single bond is basically sharing 2 electrons, a double bond is sharing of 4 electrons, a triple bond is a sharing of 6 electrons, or if we could say 1 pair of electrons. Double bond is 2 pair of electrons, and a triple bond is 3 pairs of electrons, right? Simple?
Yeah.
Yeah.
Yeah, that one, yeah.
Yeah, so, and this is, you guys are already familiar with this because you guys have already been drawing Lewis dot structures already. So it's kind of like working backwards, right? Because we went ahead of the game, okay? So this is just showing you the process of drawing Lewis dot structures. Are there any questions so far? Okay, so when we're drawing those Lewis dot structures, the way that we determine our center atom is by the electronegativity. That's how we officially are supposed to determine the center atom. So if we're given the option, right, we want to take a look at our electronegativity. That usually determines our center atom. But like in the case of where we have sulfur, carbon, and sulfur, both of those guys have the same electronegativity. Carbon would prefer to be in the middle. Carbon likes to make everything happy. Carbon's a whore. It likes to have attachments. Carbon can have up to 4 attachments, you know. Okay, you guys get that?
Yeah.
Okay, and we also know that hydrogen will never, ever, ever be in the middle, right? Because it can only form a single bond. Okay, so now let's talk about those exceptions, right? We're like, man, here we go, those exceptions. Okay, so our very, what was that, Brittany?
Nothing.
she had to mute herself to cuss so much, right? That's what she did. Okay, so let's start with the very first exception. The very first exception is when you have a total, your total number of valence electrons is an odd number. Okay, so in the case of nitrogen monoxide, nitrogen monoxide is just NO. Nitrogen has how many valence electrons?
5.
And then oxygen has how many valence electrons?
6.
So it's 11.
Okay. I usually offer a student, I'll give you $100 if you can. I'll give you $100 and you can give me $100 if you can't do it. But if you could sit there and change this any way you want to, right? That's legally accessible so that everybody reaches their octet. Then I will give you $100, but if you can't do it, you give me 100.
I don't gamble.
You don't gamble? Good. So I usually get at least one taker, and then I feel bad, and so I only take $50 out of it rather than 100, right? So it can never happen, right? Never, ever. You can play around with it as much as you want to. It will never happen. If you're obeying the rules, it will never happen. Okay, so let me tell you what you have to do in the case of an odd number of electrons, of total valence electrons. So the one who has the strongest electronegativity will make sure it reaches its octet. So they will reach its octet, but the other guy won't. The other guy will be just short of octet. So in the case of nitrogen, if we count the number of electrons around this nitrogen, how many do we have?
7.
7. And then if we count the number around the oxygen,
8.
8. Okay, so oxygen, which is stronger in electronegativity, is going to reach its octet, and the nitrogen isn't. Okay, but it's going to get as close as it can. Okay, so in the case of nitrogen dioxide, so here, both of the oxygens reach their octet. Count the number of electrons around them. How many is around this oxygen?
8.
And then how many is around this oxygen?
8.
And then how many is around the nitrogen?
7.
That's right. Okay, so let me show you in terms
And
of
that's
formal
correct
charge.
like that?
Yep. So the thing is that this molecule is very, very reactive. Both of these molecules are very reactive. The reason why they're very reactive is because they don't reach their octet, but they exist, right? And let me explain to you why they exist. So if we drew the Lewis structure, if we did the formal charges on, let's say, the nitrogen, how many valence electrons does nitrogen have?
5.
The 5.
How many lone pair around this nitrogen? Lone pair electrons.
3.
3.
And how many bonds?
2.
Okay. Now the oxygen. How many lone pair? How many valence electrons?
6.
How many lone pair electrons?
4.
And how many bonds?
2.
2.
So because the formal charge is correct, you can just leave it alone.
That's right.
Dr. Henry, but earlier you had mentioned that only anything past the 3D, they don't have to obey octet, but this group is on 2, so wouldn't they have to obey?
So I said most of the time. There are exceptions. And I also said the ones that are 3D, wait. So you got to remember what I said. The ones that are above 3D can have more than, so they could have more than 8 around. The ones that are below the 3D can't be more than 8. Okay? So yeah, I caught myself earlier, so I tried to make that correction. So
it's confusing. When you were doing, I was like, what? I was like, they're in group 2. They should obey the octet rule.
yeah, I said 99.9% of the time. This is that 1% that they don't. This is that 0.5 because there's more. There's one other.
Okay.
There'll be more. Don't worry, there's more exceptions. That's the way it works. For the most part, they obey. But when there's an odd number, there's no way that it's going to ever reach 1. Okay? Okay, so this is an example of that hypervalency, right? So remember what I told you, the ones that are in the elements that are in the 3rd period or higher? So they can actually have more than 8 electrons around. Okay? And so here we have phosphorus. How many electrons does that guy have around?
10.
Here we have sulfur. How many electrons does that have around?
12.
Okay, so this guy is called, as I said, hypervalent. Okay. And now you guys are going to really start throwing stuff at me here soon. One more major one.
One more exception?
One more major exception, yeah. Okay, so beryllium is actually a metal that thinks it's a non-metal. Okay, so that's the first thing. So if you look where beryllium is located at, it's actually a metal, but it really believes it's a non-metal. So it actually forms covalent bonds. Okay, which is really weird, right? And so, but beryllium is a metal who thinks it's a non-metal, but it only wants to have 4 electrons around it. Okay, so it is a case of what we call hypovalence. Hypo meaning less, right? Or hypovalent. Okay, so beryllium is typically hypovalent. Okay, meaning it's going to have less than 8 electrons around it. Okay, so it's always going to end up having 4 around it. So you'll see it written as BeCl2. Okay, because it can only at most will hold 4 electrons around it. So boron is a metalloid. Its metalloids have characteristics of metals and non-metals. But one of the characteristics of boron is that it forms covalent bonds. And since it forms covalent bonds, it's going to also have hypovalence. It's only going to want to have 6 around it. Okay. So if you calculate the formal charges of the beryllium, it has 2 valence electrons. This guy has no lone pair, and it has 2 bonds. Its formal charge is 0. Okay. Boron, it has 3 valence electrons, has no 3 bonds, 0. Okay. So you guys with me so far? So this guy is also called deficient. It'll be valent deficient molecules. Okay.
When we have questions, like on a test or whatever, you'll ask specifically like following octet rule or following this rule.
Well, so if it doesn't say anything, you assume that the octet rule is being obeyed. Okay. Unless you see beryllium, boron, or you have an odd number. Okay. And then usually if you see something like this, that should immediately. Fluorine will never be a center atom. Never, ever. Right? So that is like a dead giveaway. So that means that, yeah, this guy's going to definitely be hyper. Does that make sense?
So that would say that's definitely going to be hyper.
It's going to be hypervalent. SF6, hypervalent. If you have a noble gas, this guy is going to be hypervalent because noble gases already have 8 around them, right? But noble gases, when they're matched up with certain strong elements, they can be pushed, particularly the ones that are down on the period scale, right? That are below the 3rd period, right? So 4th period, 5th period, those guys, anything that's below that, they can be pushed into forming bonds. Okay. So are you with me so far? You guys are you have those looks. So, but 3 major exceptions, right? If you always count the number of electrons. If you have odd number of total valence electrons, you know it is not gonna reach the octet rule. Okay. So sometimes molecules that have oxygen in them will screw up that octet rule as well too. But they're very, very few that happens to. So I don't necessarily bring that up too much, but it's just good to know when you start getting into those complex molecules. Okay. Last thing that I want to talk about is metallic bonds. So we've talked about ionic bonds, we've talked about polar covalent bonds, we've talked about non-polar covalent bonds, and now we're going to talk about metallic bonds. Well, metals can form bonds. Actually, metals form bonds together because that's how we get chunks of metal, right? So the way that the metal forms a bond with itself is it'll actually, let's say we have sodium, right? Sodium has how many valence electrons?
5.
Sodium has 5 valence electrons.
1. It
I'm
has
sorry.
1.
1.
It has 1 valence electron. Okay, so sodium has 1 valence electron. Now, sodium needs to get rid of that 1 electron to be like a noble gas. So what sodium does when it's all by itself, sodium says, well, there's nobody around. So what I'm going to do, I'm just going to push that electron away and push it next to me, right? So then I can be positive, and then the electron will act as if it's negative, right? So it does what we call delocalize its electron. Okay. So then the next sodium atom does exactly the same thing. And so it's interacting with that negative electron, and it delocalizes its electron, right? And so then it's sticking together by plus and minus charges. Does that make sense? Okay. So if we have magnesium, magnesium has how many valence electrons?
2.
It has 2. So what it's going to do, it's going to go Mg2 plus, and then it's going to delocalize 2 electrons. So then it's going to act as if it's positive, and then the electrons are going to be like the negative to balance it out. Okay, and so they're going to look something like this. Okay, so that's in the case of sodium. Sodium is positive, the electron is negative. Positive, negative, positive, negative. So then you're going to basically delocalize your electron so that you pretend like you're, even though it's still part of you. You know what I'm saying? So it's kind of like kicking it out of the house and kicking that kid out of the house and putting it right outside, Okay?
How many times will it do that?
Well, it is only going to do it once because sodium only needs to be positive once. So it kicks out that 1 electron, and that's it, right?
Oh, okay. So like in the event of A, that example, is this like the coefficients? Like there's that many sodiums? 2, 4, 6, 8 of them?
Yeah. So, but that means, but it can do it infinity, right? So a chunk of metal, right, is a whole bunch of these guys that have done that, right? And so literally what's holding it together is just that 1 electron is acting like it's a real atom. And that positive charge that is now associated with that metal is acting like it's positive, right? But really it's 1 component. You know what I'm saying?
Yeah, I guess I got lost, or I wanted clarification on like when does it stop? Because you said it just takes 1, but then infinity. So I guess I'm lost there.
Technically it's infinity, right? Do you know what I'm saying? Long as it just depends on how many molecules you have, right? If you have 10 molecules, then it's only going to be 10. But if you have thousands of molecules, it could go on. So if you think about a piece of metal, steel, right? A long thing of steel, that's a whole bunch of molecules together.
Yeah.
Right? But can we cut it up?
Right.
Right?
can.
And by us cutting it, we're limiting to how many we're working.
Okay.
Okay? So it's just the same concept, right? Okay?
Okay.
So let me go back. So the last thing I want to talk about are alloys. So alloys are basically mixtures of two or more elements to make a metal that has like a new metallic property, right? And so all it is, it's doing exactly the same thing where these metals are delocalizing their electrons, but now we're putting different metals in there. So in the case of, let's say, we have potassium and sodium, right? So potassium is going to do the same thing. It's going to put that electron there, and then the sodium is going to be next to it, and it's going to do the same thing. Okay. And its electron is going to be here. I'll put a circle around the electron so it doesn't look like, okay? And so all you're doing is mixing the metals together, and they're still interacting that same way, okay? By delocalizing their electrons. Does that make sense? So we can get what we call alloys, okay? And some of the famous alloys that you guys may know of are listed here on the table. So 18 karat gold, 24 karat gold is pure gold. 18 karat gold is 75% gold, 12.5% silver, 12.5% copper, right? That's an alloy, okay? Brass is 60 to 95% copper and 5 to 40% zinc. Bronze, 90% copper, 10% zinc. Carbon steel, it's a mixture between carbon and steel. Pewter is 10, I'm gonna say 91% 10 and 7.5 antimony and 1.5 copper. Stainless steel is 70% iron, 18 to 20% chromium, 8 to 12% nickel. And then occasionally it'll sprinkle in some magnesium, or magnesium or manganese. Some other metals occasionally too. So sterling silver, 92.5% silver, 7.5% copper. So in that case, you're having both of those elements in there, and they're just delocalizing their electrons, but they're still interacting, okay? So metallic bonds will only occur between metals. The only exception that we know of right now is this guy, carbonated steel, okay? Which is carbon and steel. Okay, questions, concerns? Cash, credit.
Question. It's kind of before you got to the alloys, but with I'm just trying to clarify something in my own head. So
Okay.
within the group 1, 2, and 3, are those the only groups that will do this process of wanting to, shoot their?
No, it's all metals. So let's get the periodic table. But that's a good question. All of these guys will do that. So when it's just the metal, when it's just metals, they're going to do that. Now, they're going to behave differently when they're interacting with nonmetals. So when a metal interacts with a nonmetal, they form ionic bonds. But when you have metals and metals together, they're going to form metallic bonds, where they delocalize the electron. Does that make sense? So, and that's the reason why metals are solid, right? They're together, right? So most metals, I should say, are solid. We have one that isn't at room temperature.
Mercury.
Mercury, yep. Yeah, that's why he's always blued out, because he behaves kind of crazy. Yeah. And see, and that's the same thing. Bromine is also, it's a liquid at room temperature. Although the slight change in temperature, slightest change in temperature, the slightest change in pressure, bromine becomes a gas.
But bromine is not a metal, right?
No, bromine is not a metal. Bromine is a halogen, it's a non-metal. Okay, so questions, concerns? You have that look, those looks.